Um, okay, hello everyone. So hopefully we can get around the technical difficulties this time. Um, okay, I'm pretty sure I'm live right now. Yep, here's an infinite thing here. Okay, so, um, okay. So today we're talking about the holographic principle, and we're having an ongoing discussion surrounding emergent gravity. So I'm kind of taking you through the theory as we go. Um, and what we covered in the last video was we covered the Planck scale quantization. And so today I'm going to talk about the holographic principle, and I've kind of already introduced this a couple times. So today we're going into more detail. Um, and where I wanted to start, there was this man on that I met on Facebook. Um, his name is David Shiremeyer. I hope that's close to how you pronounce it. And he made these demonstrations, which I thought were really uh, like a really useful example of what I'm talking about when I discuss the holographic principle. So basically, my understanding of what he did here is he has like a two-dimensional surface here at the bottom here, and it's probably some kind of rubber. And then what he does is he sends acoustic sound frequencies at different like hertz through the rubber. And then on the other side he has like what I assume are lasers, and then he's projecting the lasers through the two-dimensional surface. And then what you see here is you see a three-dimensional projection of the acoustic vibrations on the two-dimensional surface. So this is kind of a visual representation of a holographic principle, and so this will give you like a really good idea of what I'm talking about. So basically, you have two-dimensional information in the form of acoustic frequencies, which is sound, and then from the two-dimensional sound, you're getting a three-dimensional holographic projection of that acoustic information. So basically, you're getting a 3D visual of 2D information. And with emergent gravity, it's exactly the same idea. Basically, you have information on a two-dimensional surface, and then you're getting a three-dimensional projected effect. So the three dimensions would be like space-time, and then you're getting a gravitational effect in the 3D, but it's being sort of realized by sending quantum quantum information through a two-dimensional flat surface. Um, and so I wanted to show you that um, um, as like an example, so that you can kind of like understand what I mean when I'm talking about the holographic principle. Um, let's see. Hopefully you can see me and hear me okay. Um, haven't gotten any comments yet. Okay. So where to go from there? So that's a good example. And then this is sort of a review. This is very similar to the matter waves equation that I've given you in the past. Um, so remember these F's are just like um, kind of like a general wave equation, and then I can show you the matter wave that we've used in previous videos. So let me just pull up the thing again. So this is the specific matter wave that we've been using in previous videos, and so you can see that these are exponentials, and this would be like, for example, like if you're using Minkowski space, so this like n-looking eta symbol here, this is indicating that you're in Minkowski space. And if you're using Minkowski space, then you can use these as the matter waves, these exponentials here. And then remember, this is the annihilation operator, this is the creation operator, and then you're acting on the vacuum to create and destroy particles. And then this just tells you that you're using a position vector, the x hat here. You're just using a position vector, and k is the frequencies. So you're in frequency space, right? Or k. What this nice call it k space, and then that gives you your matter wave. So this is the one that we've been using for Minkowski, like flat space-time, and we're also acting on the vacuum. So I use this a lot when I'm working with like Unruh radiation or Hawking radiation. And then this is kind of more general. This equation here is more general. So here you just have, instead of the exponential, you have f, just meaning like a wave at the frequency k, right? And then you're destroying with the a, and you're creating with a dagger at that frequency. And then I just put a hat on the side to indicate that this is an operator instead of a wave vector. Mostly because you'll notice I left the ket off of the equation here. So in this one, the wave is acting on the vacuum, which is 0, right? 0 with the hat. So that one has a ket. So in that case, it's a matter wave. And then in the more general equation, it's actually an operator because I left the ket off, right? So there's no ket here. So instead I put a hat on the creation annihilation operator. So this is kind of like a general like particle creation operator, right? And it's pretty general because you're just using these waves here. And also like I get the sense that this science is not really settled. Like once you move beyond Minkowski space, the science isn't really settled because quantum field theory doesn't really talk to general relativity. But this is sort of you're sort of like pretending that they know how. And then you're sort of leaving the f as like an abstract wave, and you're saying like, well, supposing that quantum field theory talks to general relativity, then this would be the particle operator, right? But I definitely get the sense that this science here is not really settled. Minkowski space works pretty well though, and the Minkowski space the metric for Minkowski space is all we need to get Newtonian gravity from emergent gravity. All right. So that part, I'm pretty confident that you can get Newtonian gravity from emergent gravity as an approximation. And then when you try to go more general, like as in this equation, then that's when you get into some unsettled territory that's theoretical and abstract, and there's a whole bunch of room for you to like research that and figure this stuff out. Okay, so this is basically your matter wave equation in an operator form. And let me see if there's any questions yet. Okay, nothing yet. I hope you can at least hear me. Okay, so, well, where was I going after that? Ah, okay, so basically, the idea here, with the holographic, principle, shoot, you know what? I forgot the Gauss's law equation. Let's see. You can look it up. Basically, Gauss's law is for electromagnetism. Basically, the theory is that the information about the electric charges in the 3D region. So like this would be your holographic surface, right? And in Gauss's law, if you have electric charges inside the 3D, then the information about the charges is stored on the 2D surface in the electric field. Okay, and that equation is not controversial. Now, basically, taking the Gauss's law for electric charges, and then you change the electric charges into like mass or matter, and then you change out the electric field on the surface into the gravitational field, and basically you say the same thing. All the information about the mass in the 3D is stored in the gravitational field on the 2D surface, right? So basically, that's the holographic principle. The Gauss's law is very similar to this area equation here that I wrote last time, except you have like a gravitational field here instead of like a normal vector. So here you would just have g, like the gravitational field, and then basically, like, if you integrate over the gravitational field on the surface, then you can get all the information about the mass that's stored in the bulk of the 3D. Right? So here's the 3D. You integrate over the surface, or you integrate the gravitational field over the surface, and then you get it collects all the information about the mass in the form of energy. And then the 2D is all the information that you need to get the gravitational effect, right? So that's the holographic principle. Then I gave you a visual at the beginning of the video. Elisa, if you go back to the beginning, I gave like a visual. Let me see. So here you have like the two dimensions, like a two-dimensional rubber surface, and you have like the acoustic frequency going through the rubber, and then when you shine the lasers through, that generates a three-dimensional holographic projection, right? So that's sort of like an example of what I'm talking about with the holographic principle. And we're trying to use the holographic principle to explain why gravity happens, right? I hope that kind of answers your question. So we're trying to use the holographic principle to explain why gravity happens. That's basically the idea. Okay, so I showed you. So here's your 2D surface with all the information about the gravity on it, and then you have the matter wave. And remember, what I've been explaining is that the frequencies of the matter wave for the particle are interacting with the surface, the two-dimensional surface, and then those frequencies are entangling with the qubits of information on the surface, right? And that's what we covered in previous videos. So these frequencies of K are entangling with the qubits of the two-dimensional surface, and then through that entanglement, you're generating the gravitational field. And that's how gravity, or that's how I believe that gravity is being generated as a force. It's through this holographic principle of all the information about the matter is being stored holographically on the field of the two-dimensional surface, and then the particle. So this matter wave here, this is like for a particle that's near the surface, and then those K frequencies are entangling with the qubits. And then there's one qubit. So here it's partitioned in triangles, and there's one qubit per triangle, right? And what we covered last time is the Planck scale for those triangles, right? And then this is the equation for the number of qubits, and this is due to the surface area, the speed of light, Planck's reduced constant, Newton's gravitational constant. So this is basically the number of bits per Planck area. So it gives you the total number of bits. And you could think of that in terms of like kilobytes, megabytes, but we're working in quantum bits here, qubits, right? Okay, so now with that, the next is basically you take that particle and okay, so you take that particle, and this is an example of a three-dimensional object that's getting holographically recorded on a two-dimensional surface. And so you can see that you have a reference beam here. So basically you have the laser, right? And then it's bouncing off of this mirror, and then you have a reference beam, and then when the laser splits off in this direction, it bounces off of the object, and then the reference beam interferes with the object laser beam, and then that interference of the two quantum, well, here we're dealing with lasers, right? So the laser frequencies are interfering with each other, just like with the double slit experiment, right? So like everything I've been explaining, it's all like connecting, right? Uh, um, so with just like the double slit experiment, you have the object laser beam, and then you have the reference laser beam, and those are interfering, and then you get a coherent interference pattern that hits this two-dimensional surface, and then it makes a holographic recording on the two-dimensional surface. So what I think is that here, this is with lasers. So what I think is happening is with gravity, instead of having like a laser with light, you actually have something exactly the same, except you're dealing with quantum particle frequencies, K. So these are the particle frequencies, and it's exactly the same as the light frequencies in this diagram here, except you're dealing with particle frequencies. And then what I think is the reference beam is like the vacuum, basically. And then when the vacuum gets split with the particle frequencies, then you get coherence, and then that coherence records the particle on the surface, the two-dimensional surface. All right, and then with that coherence, then these qubits that you see on the surface are getting entangled, like quantum mechanically entangled, with these particle frequencies here. Um, okay. Yeah, so that's pretty much the holographic principle. And so basically all I did next was I took from like a standard uh, optics textbook. I took a hologram, like this is the holographic recording equation, and I just got this from oh shit, I made reference 24, but then I forgot to put it down here. It's like it's basically like I could tell you which textbook. If you talk to me after the video, I could tell you which textbook I got this from. But it's basically a standard holographic storage equation using Bessel functions. And the main thing that should jump out at you is that here you have an exponential I, and then you have frequencies k, right? And this equation is very similar, especially since you're integrating over a 2D surface. So dy1 and dy2, that's a 2D surface. And when you integrate that information over that surface, then you can recover your hologram. And so basically, all I'm proposing is that you take this equation and just like like replace these laser frequencies here with particle frequencies here, right? And then with the exponential should work for Minkowski space, which is all we need to recover Newtonian gravity, right? Um, so all I'm proposing is that you take the matter wave and just use the hologram equation here, and just change it from optics over into particles, and I don't see why that should be like super controversial. It all seems pretty obvious to me. Um, but anyway, um, okay, so that's my proposal for the holographic principle. Um, and uh, and I we've already been able to recover the Newtonian gravity from the holographic principle. So taking that one step further, and trying to get relativity gravity from the same principle using these equations here. I don't feel like that's much of a leap, you know. It's controversial, but I feel like it's only controversial because it's original. Um, uh, okay, so yeah, so that's pretty much where I was going with that. Um, and yeah, okay, so let me see if I have any other comments. Not yet. Okay. Um, all right. And then I made a note. You can see this in my article. So I just screenshotted a note here. Um, basically, the main issue is getting this matter wave that's in Minkowski space over into like general relativity curved space, and then also the storage medium itself is flat in this equation. So one of the challenges is to change the flat surface over into a curved surface. Um, um, and so that's going to be a challenge. But if you're working like locally, like if you're just doing it for like a really small region, then it should work. Even if you do like just treat the spherical surface as a flat surface, it'll still work as long as the area where the coherency is happening is small, then it'll still work, right? Um, okay, so I hope I'm making sense. Um, and you can follow up with any questions that you may have. Um, and so anything that I didn't make perfectly clear, you can ask me. Um, and have a great rest of your day.